and today I'm going to be talking about experiment 4, the iodide clock reaction. A little overview of what I'm going to be talking about today. I'm going to introduce the concepts of rate law and rate constant, and I'm going to talk about the experimental procedure we went through, and the data we collected, and the conclusions we drew, and the equations we used to get to those conclusions. So to begin with, I'm going to talk a little bit about the chemical reaction we did. So it was a reaction of peroxydisulfate with iodine, and molecular iodine is a product of this reaction which causes a color change. When enough iodine is produced to react with all the peroxydisulfate, or the thiosulfate rather, that creates a blue-black color change, which is the alarm going off. Sodium thiosulfate reacts with the iodine according to the reaction up at the top. When the solution turns dark, a known amount of peroxydisulfate has reacted, setting off the alarm, which is why it's called a clock reaction. And when an aliquot of thiosulfate is added, the process continues, and we do that a few times to gather data. So for a hypothetical reaction of A plus B and C plus D, the rate would be K times A to the power of X times B to the power of Y, where X, Y, and K are all experimentally determined. For our reaction, rate is determined by measuring the amount of time required for the peroxydisulfate to react and determining the slope of plot of molarity of peroxydisulfate versus time, which I'll show you in a moment after we collect our data. The slope of the best straight line is going to be an estimate of the initial rate of the reaction, and I'll show you how we get that from the slope also. So to start with, we have known amounts given by our lab manual, the Chemistry 160 and Lab Manual honors, and I'm going to talk about reaction A. All of the reactions were measured the same way, but I'm going to talk about A. We have a known volume of the starch, Ki, etc. I'm going to show you how we did that. So we prepare reaction A. We start with the potassium iodide, the starch solution, potassium nitrate, the EDTA, and the ammonium persulfate. Then we mix, and the reaction begins. After you mix and wait for a little while, the blue-black color change is going to happen. This is what it looks like in real life. And once the solution turns blue-black, the time is recorded, and a second aliquot of the sodium thiosulfate is added to the mixture and swirled until it becomes colorless again. And that's repeated until we've done 6 aliquots. So here's the raw data for reactions B, C, and D, but I'm going to be talking about A. So you can see I circled the slope, and that's what we're going to be using to find, that's what we're going to be plugging into our equation. So we put the slope over the volume of the starting reaction mixture, which we got from the lab manual, and we end up with 4.21 times 10 to the negative 7th moles over second divided by 0.02 liters. And we end up with a rate of reaction of 2.11 times 10 to the negative 5th molarity per second. Now we need to get the concentration of the peroxydisulfate and the iodide. To start with the peroxydisulfate, the calculations for experiment 1 or experiment A are shown below. We have the known amount of peroxydisulfate solution that we were given. We have the initial amount of peroxydisulfate, the concentration of the stock peroxydisulfate, which was on the bottle, and we end up with a molarity of 0.05 for the peroxydisulfate. We repeat the process for the iodide, and we end up with a molarity of 0.10 molarity for the iodide. And again, this is going to be different for each of them, but we're talking about A. So now we have the rates of reaction and the molarities for iodide and peroxydisulfate. Now we need to calculate the rate constant. It's important to note that this is a first-order reaction, as that is going to determine how we determine the rate constant. So the generic rate constant equation for this equation is going to be K times peroxydisulfate raised to X times iodide raised to Y. We're going to start with the peroxydisulfate equation. So what we're going to do is we're going to use C and B experiments because C and B have the same iodide molarity, but they have different peroxydisulfate molarities. And because they have the same iodide molarities, we can cancel them out on top of one another. Shown here. We cancel out the K and the the iodide concentration. We're left with the peroxydisulfate and the rate. Once we have that, we can plug in our numbers here, And again, this is the rate of reaction we already determined in the previous slides and the molarities we determined in the previous slides. Plugging those numbers in, we're going to end up with x equals 0, which means this is a zero order reaction for the peroxydisulfate, which means that any molarity of peroxydisulfate will be raised to a 0, which equals 0, which negates the value of the peroxydisulfate. We're going to repeat the process with iodine, and again, we're going to be able to cancel out the peroxydisulfate instead of the iodide this time because we're using reactions A and B. And A and B are the same molarity for peroxydisulfate and different for iodide this time. So we can cancel out the peroxydisulfate. Plugging in those numbers for the rates of reactions and the molarities, we end up with y equaling 1, which means it's a first order reaction for iodide. So our generic rate of reaction, once again, is K times peroxydisulfate raised to X times iodide raised to Y. And because peroxydisulfate was raised to a 0, we're going to go ahead and cancel that out. So our actual generic rate reaction will be rate equals K times peroxydisulfate raised to the power of Y. And once we move that around to equal K, we'll get rate over peroxydisulfate raised to Y equals K. And because peroxydisulfate raised to 1 is just the number of the molarity, I didn't write it because anything raised to the power of 1 is itself. So to solve for A rate constant, we're going to go ahead and plug in the rate of reaction over the molarity of iodide, and whatever that equals is going to be our rate constant. So we go ahead and get 2.11 times 10 to the negative 4th, and that's our rate constant for A. We repeat the process for all of them, and you can see we get very similar results for all, which indicates a low error margin. So the rate law of the reaction is determined previously in the experiment to be K times iodide raised to the power of Y, but again, because it's a 1, it's going to be, you don't have to write it because anything to the power of 1 is just itself. After we establish that peroxydisulfate is raised to the power of 0, we know that that doesn't have to be included in the equation because it's just going to end up as 0. And generic rate law for the equation, again, would include the peroxydisulfate, but because we got rid of that because it's raised to the power of 0, we end up with rate equaling K times iodide to the power of Y, 1. So possible sources of error for this, there's a lot of sources of human error for this experiment because when you're measuring color change visually, there's a lot of room to have a couple seconds of error if you don't notice it right away, or if you measure it from the beginning of the color change as opposed to the end of the color change, you have to make sure those are constant. You have to make sure you hit the timer at the exact right time. So there's a lot of sources for little time errors, just a lot of human error in this experiment. And then also inexact time readings, because if you don't hit the button at the exact right time, you might end up with a couple seconds off, and that could throw your data off. Thank you very much.